So if you weren't here before, I'm Manny, replacing Manfred again. Amazingly enough, we are going to do introduction to this talk, which is right after the course. So we'll talk about information theory and things like that, and codes. No, we won't mention codes, but they are there. Shannon would appear. So if you don't want to go there, let me just tell you there is an apero. It's not written, but there is an apero later. So, yeah. I'm going there. I hope you will join me. That's one thing I wanted to. So we are talking about information, about entropy. And the nice thing I wanted to just to read out is this, attributed to von Neumann. Hello. Nobody knows what entropy really is. So in a debate, you will always have the advantage. So no one knows that. And that's actually how they chose it. So another thing here. Yeah, so Shannon was not very clear what to do, so how to call it. He wanted to call this uncertainty here, because that's what it is, more or less. But then they discussed with von Neumann and said he had a better idea. So uncertainty was actually taken, uncertainty function, principle, and then he said nobody knows what entropy is, so why won't you call this entropy? It's not really, it's taken, it was taken by statistical mechanics, but yeah, no one still understood what it is, and it's changing or not changing. Yeah, so, and let's also show you the book that you can use. This is online. This is another Eisenlehr Ward with Lindenstrauss, which are still in writing, but it's more or less complete. Definitely chapter 1 and 3, which is what we will talk about, I think, is definitely complete. We will talk about chapter 1.1, hopefully also 1.3. Okay, so I will try to use the same notation after at least we have some kind of introduction. Okay, so we start. So as you understood, we are going to talk about entropy. And the idea is to take a measure-preserving system. For now, I won't write the sigma algebra. So now I'm writing it, but normally I won't write it. Measure-preserving system, maybe the measure I will write, and okay. And our goal is to attach a numerical invariant. Numerical invariant, okay, which we will try to figure out together what this should code for us, what this numerical invariant should be. But when I say invariant, it's important to specify what I mean. I want this to be isomorphism invariant. And I think I need to recall what is isomorphism of dynamical systems, no? Makes sense. Right? So if I have a dynamical system, I have a map going from x to x, which is measure preserving if I'm talking about what we're talking about. But I can have a different system, okay? And I might find a measurable map. So, okay, I'm allowing myself to be, not to write everything because it's just an introduction. A measurable map, invertible, also almost everywhere invertible, not invariant, invertible. Invertible, such that this thing commutes, okay, the dynamic commutes. That is what I would call an isomorphism, because it's invertible. If it's not invertible, I will call this a factor, but still commutes, I will call this a factor. This was already in the course. No, yes. It was never in the course. Let me do it properly then. Okay. Of course, yeah. So again, x, t, x mu, t, y, nu, s are isomorphic. If there exists phi from measure preserving, by that I mean if I push the measure mu, which was defined in the course pushing measures, yeah, I get the measure nu, okay, and this, what I drew before, commute. Commutes, which let's spell this out. If I do T and then I do phi, is like doing phi and then to do S. Okay? A measure preserving invertible with this thing. Okay? So automatically also the inverse would be measure preserving if I have this. And okay, I will not need it today, but Marcel will need it today. If I remove the invertible, right, then I just write here, yeah, maybe. Let me write this out properly. Same definition, with without invertible, without phi being invertible, say that, so this definition, it says that y is a factor of x. So it can be that this is not an invertible map, so we see here some dynamics and we see here some bit less of dynamics. It's like going down. It can be very well that this is just one point, and this is the identity map, so it always commute. So any dynamics factors to a very trivial dynamics, not interesting dynamics, which makes sense. But if this is invertible, then the dynamics here and the dynamics here is the same. And what I would like to do when I say that I want a numerical invariant, I mean that I would, if I attach this number to this system, and this is isomorphic to this system, I should get the same number. Okay? So this means, so so this will be the name of my numerical invariant, then I want that if xt is isomorphic to ys, then I want that, let's say with mu as before and nu, I want that this xt would be equal to ys. That's what I mean by numerical invariant. Because the origin of that, okay, I will say what is the origin of this question. Is this clear so far? I was not preparing it. Okay. Because the origin of this question comes from here. Question. So the origin of this numerical invariant comes from the following question. We have, say, 0, 1, z with a shift map, and the measure mu half-half. So let's call it mu2, which is the half-half measure. You know what I mean by that? Right? I give 0 half, 1 half, I take the shift, the usual thing that you take in such a shift. Okay? I do the same with free elements. Same thing. Also the shift, and also I take this time also the uniform measure. Yes?
Is it enough to ask for phi not to be invertible, or do we want it to be injective but not surjective?
I want it to be really invertible up to measure 0, because I'm...
For the factor thing.
Does it have to be surjective? So definitely not injective. Do I want projective? Do I want projective? For you, you're not looking. I think I want almost every, so up to measure 0, that to be projective. When we talk about it, I'll talk about it. So yeah, thanks. I think I want projective. Yeah. I want that I'm hitting everything but measure 0. That's true. Thanks. So let's go back here. Yeah. So here is a question. If this is x and this is y, does this system, x with the shift, y with the shift, are they isomorphic? You might say that it's a bit weird. Why would they be isomorphic? This is 3 symbols, this is 2 symbols. So let me give you a few facts. They are spectrally isomorphic. What do I mean by that? So as far as functional analysis cannot tell them apart somehow. So maybe I'll write a definition which we won't use. So just that we just spell out what we mean. There exists some linear map from L2 of the first one to L2 of the second one, linear, such that I have that if I take F and G here, then their mu L2 here, inner product, is equal to their image under W for mu free. And also if I have L2 of mu to x, L2 of mu free y with W, and here I take this coupon operator, U of this shift, let's call it T, and also let's call it also here UT, then this commutes. So as far as these function spaces can tell, these are isomorphic. That's one, and they are both mixing, and they share many properties. They are definitely isomorphic because both are isomorphic to 0, 1, to the interval. So spaces is binary expansion and ternary expansion. Here is another crazy fact, right? Let me just write it a bit. So the shift of 4 symbols when I take the measure, the uniform measure, and I take the shift, this is one system. And if I take 5 symbols, and I take half, and here I'm taking 1/8 with a shift. Amazingly enough, these 2 things are isomorphic. So it's not out of the question that these 2 things are isomorphic. Okay? And if they are isomorphic, this numerical invariant that we are looking for will be the same. And if this numerical invariant that we're looking for will be different, then they are not isomorphic. Okay? That was the motivation for that thing. So what this numerical invariant should be. Okay? And then, as we said before, no one knows. So whatever I'm saying should be correct, right? So no one knows what entropy is. So this numerical invariant, what are we looking for? So I'll tell you what are we looking for, but then I'll go to a simpler question to motivate it. So what are we looking for is that we actually have a process, right? And we think about T as something that we apply again and again. So when we say time, we mean application of t again and again and again. So t to the time, okay? And our question, the numerical value that we want to take is to measure, yeah? So if we have a system, again, h mu t a system, the numerical invariant that I want to attach to it, I would write it this way. This would be called entropy. Whatever this thing is, I want this to be the rate in which we lose information over time. Because it's a rate, so every time I apply t, how much information did I lose? Okay? What is information? Information is where am I in the space. T does something in the space. Information is where am I. Okay? What can I say about this? And if you believe me, then high entropy, would be related somehow to chaos. Because chaos is exactly what we are mean when we say chaos. We exactly mean if I do a bit of a change, I don't know where I would land. It's undeterministic, okay? I lose tons of information. It doesn't matter where I am now. One iteration, I'm lost, okay? And zero entropy, so this thing would be always positive or equal to zero. So zero entropy should relate to order. So it could be a very complicated dynamical system, but still it would have some property that if I know where I was in the last 10 years, I will probably know where I am in the next year. Okay? So that's the idea that we are looking for. But before we do this, let's first take a space, and take a partition of this space into small bits, and talk about the entropy of a partition before we try to figure out what's going on here. Entropy of partition, and for that I want to play a game. It's a game, my kids are slowly too old for this, but there is this game. I tell you that I think about a number and you need to guess it. Okay, so I'll give you hints. I think about a number between 0 and this number. Go on, guess it.
73.
That's true, actually. How did you know? He actually knows me too well. I'm surprised. Very good. You wouldn't know my story. Good. Why did he know this? And this is a part of the story that comes later. If I play with this with my kids, slowly they know me, but before they knew me, they thought I would be taking the uniform measure. That each point has the same mass. Okay? But my plan was to ask you, do I think about my favorite number? So I think about my favorite number, so it's not uniform anymore, so it will be mu of many. And actually, mu of many is a very simple measure. It's equal to 1 if x is equal to 73 and 0 otherwise. So in some sense, okay, you just ruined my story. So at least what we learned from that, and I think it should come in 5 minutes, not now, that the question is also related in terms of information about how are the numbers are split. Okay? And I'll say that intentionally I think about the uniform distribution, and I think about the number. What will be a more reasonable question? And the question is yes or no. So the question can be, is it 73? Okay? If the guy knows me, it's a very good question. But if you don't know me, and I'm, okay, now you know me, but I insist, I take the uniform measure, what would be a good question? So will the question, is it 73, would be a good question? Quite stupid if so. Yeah? So kids actually, if we do it from 1 to 10,000, they would stay low. Okay. But as a mathematician, what would be your first question? Try.
I mean, if it's one number uniform with the dark measure, then just try half into binary search?
Well, one question. Binary search is an algorithm. One question would be cut it into half. So are you asking is it bigger or equal to 64? That's your question. Oh, yeah. 63 then, if I wrote it this way. Half-half. It's a good question. Another good question, maybe? Okay, you're not, it's too easy for you. What's a good second question? This is the first question. We gained information from that. Okay, it's smaller than that. So it's here. Yes? If it's even or odd. Why this is a good question? Okay. So if it's smaller than 62 would be a stupid question. Again, if you know me, 63 is another number I like. Okay. yeah, completely. And because some of these are independent from each other. Okay? Let's see. Now comes the idea that this is only under the assumption that I take the uniform measure. Andre ruined it for me. If I ask you about my favorite number, it's what's written here. If I ask you about my favorite number, then you might change at least you say, is it a prime, if you don't know me that well. But if you know me that well, it's like the biggest, strongest prime ever, or something like that, which is stupidly enough 73. It's very stupid, but I think it was in this television show at some point. Good. So we see, thanks, Andre, that this is related to also the distribution itself. So if the question is something is a good question or not, it's very much related to the distribution of the measure on our set, right? So if you think favorite numbers should be primes, then you would ask me if it's prime or not. But if it's uniform, it would be quite a stupid question, not too many primes. Okay? Good. We all agree that questions, so yes and no questions are somehow related to partitions. Partitions into two sets. Okay? And what actually I want to do, I want to talk about the entropy of any partition. I want to define it, and I want to motivate this definition. Okay? So I would call it, so if P is a partition, if it's a partition, I will call this entropy H of P. Okay? And I want to define it as somehow the information that it contains somehow. So before defining it, I would ask myself a question. I would go back to the question there. What should be the entropy of this partition? So partition into singletons. Every number is its own element in the partition. So whatever this thing should be, this is all the information that we want. If we are trying to measure information, how much information is there in our partition? Okay, so actually maybe, and it's all the fault of Andre. It took me out of my planned route. So there are two things that I wanted to talk via these questions. So I want somehow either to think about the amount of uncertainty in P, okay, or the amount, this is actually better to think about it, about of information gained by performing this question. So if it's two sets by performing this question, but if it's many sets, I can think about it as an experiment. The amount of information when someone comes and tells me you are in this specific element for all elements gained by performing or answering, yes, no question, performing the experiment. Again, I think about any partition as an experiment, outcomes of possible experiments. So if I take this thing with me, here I should get all the information. Because if I perform this experiment, I know where I am. So if you are allowed to ask me, in which element of this partition is your favorite number, we are done. Okay? And if I take the uniform measure, everything will be here defined with respect to uniform measure. Yeah? So will be defined with respect to a measure, and now I want to take the uniform measure. Not always, yeah, but now I want the uniform measure. I can think how much information is there here, and for some reason, if I was named Shannon, he wanted to play exactly this game, and he decided that here would be the number of yes, no questions, the minimal number needed. And so what's the entropy of that thing, the Shannon entropy of that thing? How many yes and no questions do I need to decide where I am? If you are not trying to do bullshit, you're really trying to, you first do half like that, then you do half differently, and so on. How many yes and no questions do you need? Let's think about it. Yeah? 7. Why 7? Because I exactly chose that all the numbers here are, their binary, every number here is in the binary expansion. Is this what you chose before is to tell me, to ask about this, or is this 0 or 1? And then even and odd, can we see it from here? Yeah, if this is 0 or 1, this was the other one, and you see that it's independent. And you could ask me slowly, it's difficult to say exactly what it is, but okay. So you need 7. And 7 would be also the log 2 of 128. Okay? Good. So this is Shannon entropy. And the last thing of this introduction, we should start at some point. Maybe it would be a good idea to start properly. The last thing that, let's call this again, how much entropy a la Shannon I have for the first good question. So how much amount of information did I gain by asking the first question? Now we have a unit. This is 7, right? So how much did we gain? Yeah? We should gain exactly 1. And then I can ask a different question. Good question. But let's say that I had the first question. And I can make something like entropy conditioned on the first question. So if I go to this idea, given that I know what happened before, how much information would I gain by asking the second question? So for example, if I'm very stupid, I'm asking the same question. Same. How much information should I gain? No information, because I already know the answer. But again, it's a good question. What is this? Yeah? So a good question, now we understand this should be, again, 1. If I did a good second question, and for example, the even odd thing was a good second question, now asking about this would be a good second question. If I start to say, is it bigger now than 30, it will be okay question, but not that good. Okay, so that's, and I want to measure at each step what happens. Are we ready to start? Okay, so now we will just start 1.1 of the book, but this intuition should always be there, because otherwise it's a lot of symbols, and I'm following the book, so it's Xi and Zeta, which looks the same, and Chi, okay? And I cannot write them very well, so yeah, we'll see what happens. But if we have this intuition in our head, and we go back to it all the time, it would be helpful. Yeah. So again, the structure is, my goal is to define this invariant. I would start with playing with partitions. There won't be any dynamics, like we just did. Once I'm done with partitions and I understand too much about partitions, I would go to dynamics and see what happens. Okay? So let's start strong of notation. I'll try to be more organized than before. I have x, again, normally I won't write b, yeah, and I don't have any dynamics yet. Okay? And I have a partition, so, and this partition is C, that's my C, and for later use, that's my zeta. Okay, whatever it is. I have C, which is either a finite partition like the one that I just erased, or a countable one. Okay, and if I take an element x in X, I can ask about the atom with respect to C, that's my notation, and this is just the partition element containing X. Yeah, so if it's not clear, it's the same place, good, here is our partition, and say that this is A1, A2, and my X is here, so this is just A1. Okay? It's nothing fancy, it's just a lot of notations. Okay, let's be a bit fancy. I want actually to identify, and it will be very useful later. I don't know, we have 2 more weeks. I'm not sure how much later we have. But it's good in any way to identify partitions and corresponding sigma algebra. So I would write this to the sigma algebra generated by the partition element. Okay, I just need to make it into an algebra. But if you want, I can also say I take all the sigma algebras containing elements of my partition, and I intersect. And the minimal one will be denoted by that. I would write it in a second. That's one notation. And here it comes. I have Xi and I have eta. And both of them are partitions. Eta is now B1 up to B2, maybe finite, maybe not. Anyway, countable. Then I want to define this eta, so Xi doesn't matter, it's commutative. Xi eta is the partition, with AI intersected Bj. Yeah, you understand, for all I and all j relevant to be in the other partitions. All the intersection of the 2 partitions. Okay, it's the join, I say Xi join eta. You really stop me if I don't make sense at some point. Okay, and yeah, it's a small exercise, but it's quite easy, and I will just define it. If I take the sigma algebra generated by these 2 things, would be just the sigma algebra join the sigma algebra of that. By joining sigma algebra, I mean the intersection of all sigma algebras that contains beta, that contains the sigma of Xi and sigma of eta. So, okay, you cannot see it, but let me write in complete generality. If I take the join of countably many partitions, yeah, I just mean without sigma, all with sigma, I just mean intersection of all. Right, the minute I have countably many, it might not be a partition, might not be a countable partition anymore. Okay, so I take intersection of all sigma algebras such that the sigma algebra is containing, it doesn't matter if I write here the sigma algebra generated or not, yeah, for all n going from 1 to infinity. Okay, so in particular, I define it also for 2. So I don't care if infinity is equal to 2, then I have this definition. Yes?
Should we write a sigma on the left side?
Yes and no. Because again, I want only countable partitions. And if I take a join of infinitely many countable partitions, say I do 1 over n, so I take 0, 1 and divide it into 1 over n for every n. The join of all that, okay, is the Borel sigma algebra. So it is a partition in some sense, but it's not. So once I do it for infinitely many, I automatically want to define it as a sigma algebra. So I take intersection of sigma algebra is always a sigma algebra. So that's the way I define it. This is either an exercise or a definition. And here it makes sense only if I write it this way. Okay? Good. And last thing we need is the inverse of, if we had a map from x to x, which will we have later, but didn't say anything about it yet. I take a partition here, so I can define this as T inverse of A1, T inverse of A2. Remember, C has this A1 up to, and so on. So I just take the inverse images of a partition, the partition element. I do get a partition, you agree. Every element lands in some partition element. It's in the inverse of some partition element. Agreed? So that's a definition of a notation. We have enough notation, I think. Yes. Okay. So I don't mess it around. This should be here. I was definitely optimistic. And again, the definition that I want to give now, I want to give a definition of entropy of a partition, would be the amount of uncertainty or the amount of information gained if I tell you in which partition element I am. Okay, that's what I want to do. Okay, so definition. This would be entropy of a partition, which again, the amount of uncertainty, the amount of information gained. I want to define it. So again, the same setup as above, and I define the entropy with respect to mu of a partition, okay, to be the function h, which I'm now defining by giving you this definition. I would take mu of A1, mu of A2. Okay, I just put this now just a function of numbers, right? It's a function on sequences of numbers, and I define it to be the sum of minus mu AI times log of mu AI. And the sum here is all the relevant i's. I'm going from 1 to n if it's finite, or 1 to infinite. So to infinity if it's not finite. And again, if this was a number B1, B2, B3, so I would just write these numbers here. Okay? And I need to say some things. This could be 0. This could also be infinity. And I need to define for you what is log 0 log 0. I define it to be 0 because of the following. This would be the most important function today. This function x log x looks like that. And here it's not defined, of course. So let's define it to be 0. Okay? So that's what I do here. Because I can have a partition element, which is trivial. For example, if my measure is the atomic measure on 73, yeah, so everything that does not contain 73 has 0, right? Shannon would have put a 2 here. It doesn't matter. We are not computer scientists, most of us. So we don't put a 2, okay? But if you would have put the 2, we would get this exactly what we were saying before. So we have this function, and I also want to define the entropy of C given eta. Now I have, again, with respect to mu, okay? I want to define this, and this should measure what we were saying that this should measure, right? And how would I define this? So I would write a definition by the right way to think about it is that I take each of the atoms here, each of the partition elements here, I do entropy only with respect to this guy, and I do it for everyone, only with respect to themselves, and I take the average, the weighted average of them. We will see it now. So what I want to take the sum, okay, of mu of bi multiplied by mu of, so, yeah. It's much better to think about the level definition. Now I need to think about it to do it, right? So this is mu of A, right? So here I'm summing over the BIs, and here I should sum over the, maybe infinite, maybe n, over the AIs, BI, mu of BI, yeah, what? Okay, let me help myself. This would be the entropy. Here is the definition that I need to write it properly. So this is what I said before. I take this, and I take mu of BI, and now I want to write the entropy, okay, of the measure mu restricted to my BI of the partition here, restricted to the BI. So now that's the definition I really wanted to take. Now I need to write it properly. So this I copied properly. Now I need the entropy of that thing. What is that? So this is the measure. Yeah, so let me write it properly if there is a mistake there. Yeah, so this should be, so my measure is mu restricted to BI, so this should be this measure. So this is the measure of AJ intersected with BI times the log. Okay, but the measure here, so it actually was correct. So the measure here, I need to normalize it to be the log of BI, yeah? This is the measure. Not log. Log is not coming yet. Okay, good that the break is coming. And now log of the same thing, of the same number. It is complicated, as I can think, but again, the idea is not complicated, so if you get it correctly, and you don't forget the minus, because the minus there, so it goes out, then this should be actually correct. Yeah. Okay, I understand now. Stupid me. And this goes out with this one. So one could write out this definition, but to show that this is what I told you it is, okay, stupid me. Okay, so one could take this thing as the definition because this goes out with that thing. To show this is what I was claimed it to be, a weighted average of the entropies of these restricted measures to BI, one should introduce this thing inside and show that it's equal to that. So actually, I didn't mean to do this. So I did it because I forgot the definition. Okay, so this is the definition of this restricted entropy. And if you want in the break, because I won't do it, you can take all the examples that we did with the Shannon, with good and bad examples, and if you just use log to the basis of 2, you would get exactly that. Yeah, actually, let's just do this before the break for fun. If I take h of the uniform measure of the partition that I said before. So this is officially break time, but 2 seconds. Okay? Just do one calculation. What do we get here? What do I need to do? This is this kind of definition. This is the sum of minus of 1 over 128. Right? This is each one is uniform. Right? And I need to multiply this by log of 1 over 128. Okay? And I sum it from I going to 0 to 127. So I sum the same thing, actually, 128 times. Okay? This minus goes inside the log, so it flips. And this is always the same. So it's indeed log of 128. So actually, I didn't know about this, but if you do log 2, then naturally you call this 7. You call this is 7. You call this 7 bits. Okay. If you do the natural log, then you call it NAT, which is natural units of information, according to Wikipedia. So, but this is a number where the Einheits, where the units are just, yeah. But anyway, it's log 128. Calculate, for example, in the break, what is this of even and odd? Or the other one, what if you do even and odd, but you think about, yeah, let's go to a break. I'll write exercise here. As a question for the break, right? This should be 1, or it should be maximal. Yeah, you can try it out. Yeah. Thanks. Okay, so this is definition. But again, I told you I keep forgetting this definition because the definition I'm thinking about is that I look at all the B, here it's BJ's, mu, I don't know now what is J, what is I. Yeah, I changed it now. Okay, so here it's BI. Mu of BI, which is related to here. This is the B's, this is the A's, right? And I actually take the entropy of which measure. I take my measure that I started with, and I restrict it to the BI. And I take the measured partition, what I'm trying to measure the information, and I restrict it to BI, where, again, let's define this object, where the measure restricted to BI is just, the partition restricted to BI, this is just the set A1 intersected with BI, A2 intersected with BI, and so on. I just restrict everything to this BI. And when I take a measure, I always like probability measures. Okay, I take a probability measure, and I restrict it to a set. So I can only do this, and I would only do this, I don't care about the zeros, zero log zero thing. If I restrict it to this, so I want to just take my original measure, and ask, okay, what does this do for a set A? So it just takes my original measure and look at A intersected with BI. Okay, but this would not be probability anymore. To make it probability, I normalize it by the measure of BI. Okay, and it only makes sense if you don't want infinity and something like that when BI is not 0. When it's 0, then I just use this definition. But it's all the interesting elements and their respective entropy. So it's a definition, it works. So if you did the exercises here, a good exercise was also, yeah. Let's see that you are following me. If I would ask you what, I should maybe make a calculation, but let's see if you are following me. If I take a partition and I restrict by the partition, which is all my space, so okay, it's one partition element, what this should be? How much information would I gain by knowing that I'm in my space? No information, right? So this should be, so the new information that I get from here after asking this question is exactly the same amount of information that I would have gained, right? If I would just ask this question. So when I restrict to this thing, so this, you can calculate it, and you can also just believe it, because it must be true. Okay? Good. So that's a remark. I told you about Shannon. Okay, let's try to be a bit quicker, see if it works. I will just tell you a bit of a story. At least, we proved this at least. So you see the function h. This is defined on sequences of numbers if I have countable partition, or on finite things if I have finite partitions. Okay? So I can actually define, just as a curiosity, I can define this simplices, right? This would be like P1 up to Pk, so it's a sequence of k numbers that they sum up to 1. Up to k, they sum up to 1. And I can take the union. So I can define the simplices as the union of all simplices for k, for all k in n. Okay? And I have my function h that I defined above going from here to 0 or maybe infinity. Okay? This just takes, say that it takes P1 up to Pk, this goes to the sum of minus Pi log Pi. This is the function h. Okay? And apparently this is the good candidate that we will get if we wanted to do this information, this uncertainty. Apparently this is the entropy function. If you are not a dynamicist, you would be very interested to know about the universality of such an object, right? So we already saw that we could take log 2 instead of natural log. But otherwise, this is an universal definition. This comes from the following property. This is the unique and therefore it should be special function with the following properties. First, this is always bigger than 0 and equal to 0, you have equality. When do you think it's equal to 0? It's related to my favorite number, 73. Okay? If I have a measure, where I have an atom that takes everything, if I have a part of my partition, okay, which has measure 1, what do I get? So see, if one of them is just 1, then all the others are 0, right? And in this sum I get 1 times log of 1, which is 0, plus 0 times log of 0, which I define to be 0, so I get 0. Okay, and it's exactly what happens if I have some, dictator. Say, this is the only important point. This is the only important partition. So this is 0 if and only if there exists I0 with Pi0 is equal to 1, and all the rest are 0, then because they sum up to 1. Okay? One property, second property, again, just to write a correct mathematical statement. This is equal to the same thing if I add a 0. So if I have such a function that has 1 and 2 and 3, the maximum of h of, say, let's call it x in with k numbers, this should be log k with equality if and only if my x is just 1 over k, 1 over k, 1 over k. Okay? K times. And this makes sense. Which partition would have at most uncertainty? Which partition would not favor one to the other, so we know very small? Which partition is interesting if we perform it and ask about the information? It's the uniform partition. It's the uniform measure somehow in some sense. Every element has the same weight, then there is the maximal amount of uncertainty. So apparently, this is the only bit which is not abstract. I tell you, this is the unique function, so it's also true. I will prove it today, hopefully, that the maximum here is indeed log k. And if it was Shannon, then it was log 2 of k. That's the only difference. So then if I put log 2 of k, then I get the definition of Shannon. And the fourth thing is the following. If I take the entropy of a join of two partitions, yeah, so what this, again, you could guess it if you think hard, right? So I want to say that here I should write something. Okay, so what is the entropy of the join of two partitions? So here there is more information, right? It's a much more delicate partition. So how would I compare what I got from the first question to what I get of asking both of them? Okay? What should it be, right? So I asked the first question, I got this. Then I asked the second question, and together I got this. What is the difference? Yeah? Yeah, how much information did I get from asking the second question after asking the first? Okay, so you could have guessed it. And once I have these four properties, we will not prove it. It's not even in the book. So the book is apparently, I was told that you don't, so you can Google it, but it will be on the website. It's the second book that Manfred and Tom Ward and Elon Strauss are writing. And it's also not there, but you have a reference that this was proved by Hinchin. Okay, let's prove something interesting about this. Let's prove this maximality, right? Let's prove that at least, so our goal is to show that our function satisfies that. The uniqueness we will not show, but we want to show that our function satisfies that. I think 1 and 2 are trivial, 3 and 4 are not trivial. Okay, and I want at least to do this. I thought I want to do more, but that's life. It's amazing every time how much time this thing takes. Good. What lies over all the arguments here is some kind of a convexity argument. I want you to note, before I start even, x goes to x log x. As I said, it looks like that. It's very much, right, if I call this phi, then the second derivative of phi is 1 over x, which is positive for x greater than 0. So you remember this from analysis? If your second, then you drive to the left if you drive on the, right? That's what it means. The convexity, and the same holds for x goes to minus log x. The second derivative of minus log x is 1 over x squared, which is also positive. For that thing, this implies the following that you might know, don't know. You can, for this function, but you can forget it if you want for now. Let me put a definition. I have an interval in R, and I have a function phi from I to R, and this, I call this function convex if, phi, when, so I have elements x1, x2, x3 up to xn, okay, in my space. I want to take gewichtete Durchschnitt. I say today 10 times. No intersection. Weighted average, thank you very much. I want to take a weighted average of them. And this would mean I would multiply them by ti, and I would sum them up, and I would assume that the sum of the ti's, because I want it to be average, I would assume that this is 1. And I want to ask, where does phi, so I know something about the x size, I want to ask, where does this element go? 1 up to n, say. And this would be convex if this is smaller or equal to taking the same weighted average of the images of xi's with respect to the same weights. Okay? Where the sum of this thing is 1. This would be convex, and you should play with it. This is a convex function, indeed. Somehow it means that if you take the second, how do you call it? Secant of Deutsch. If you take this thing, it's always higher than the graph itself, which is what we see also for our function. And I want to prove something about this, which is called Jensen inequality. For that, I would need to play with this thing a bit. So let me play it. So it's just a remark. I would take some t where I would have my middle somehow, and I would take an s and the u around it later. So I want first to tell you something about phi of the middle point. So in order to say something interesting about this, I would just say that my middle point is the weighted average of these 2 points, right? If I have these 2 points, if I write correctly my weights here, I would manage to make it into weighted average. And if I do it correctly, here I would have t minus s over u minus s, multiplying my s, and here I would have the analogous thing, u minus t of u minus s. If you open the parentheses here, this is exactly the weights to use this idea to write this thing. They sum up to 1, okay? This is the way I would write my element t here. No one complained yet, maybe because there's no chocolate. I have phi here, and then by convexity, if my phi is convex, yeah, then this means that this is exactly this weight. Multiplying my phi of s, and the other weight multiplying my phi of u. Okay? And if I organize this, do a bit of algebra to organize this, I would get something that I would like to use, and you should be able to see why this is. Again, I write phi and I think about phi. Var phi. T minus s, that this is smaller than phi. I don't want to make mistakes, but I could have guessed it because this is what I want to do, and let me tell you why I could have guessed it. Yeah, up to writing the correct phi. I could have guessed it. Why could I guessed it? Because it's some of the derivative before and the derivative after. There's a differential quotient that I have before or after. So if my t is somewhere here and I have this tangent, I take the differential quotient here, differential quotient here, and that's something that I expect for functions that look like that. In any case, this is a direct thing from here to here. It's just reorganizing, and I would need to use it. Okay? But if I want to remember it, it look like in in the order of taking differential quotients, which is actually what the next proof will do. And this is all, we are doing all that to prove what I'm just erasing, to prove 3. And maybe then later to prove 4, to prove this maximality. And what we will use it again and again, so it's good to do it. It's also good to see this proof once. So the proof that I want to do is a lemma in analysis called Jensen inequality. Yeah, we'll do the full generality. I hope I'm not spending too much time for that. We could have done it. So we could have done it for a differential map, which is our map is more or less like that, but we do it for continuous map. And then it's a bit more difficult. We'll see, maybe I'll cut it. No, I'll cut it a bit short, but at least I give you the idea. So I have an interval. Yeah, and I have phi from this interval continuous. Okay, and I have a measure space, x, b, mu, and I have a measurable map. Yeah, f to my interval, measurable map, measurable. And I assume that my phi is convex. Yeah. And it makes me think that I forgot to tell you something. This is the definition of convex. And if I really wanted, so I actually need it. Sorry. If I want to add respectively strictly convex, then it would mean that I have a strict inequality. And then, unless it's the stupid thing that I take the average of the same element. Okay? So, unless my average is very, very stupid, then I have strict inequality. Right? So, because I cannot have always strict inequality, I can take all of them to be 0 and one of them to be 1. It would be very weird to have strict inequality from identity. Okay? So, I assume that phi is convex, or I will just prove the convex, but there is the same version when it's strictly convex. Measurable, say, sorry, in L1 of mu of x. And what is very important, that x, so mu and mu of x is 1. So it's a probability space. Okay? So the picture is that I have a probability space. I have, this goes to an interval I, and this goes to R. Okay? And this function is convex. The Jensen inequality says the following, somehow generalization of what we had. Phi of the integral of fx d mu x is smaller than taking the images. It's just a generalization in some sense. F of x d mu x. And if I would write strict, if I would put here strict, then I would put here strict. Okay? That's okay. Let us do a proof that least gives the right idea, and then it's a nice thing to make it into a real proof. How should I think about this map F? Right? So it's a map to the interval, and it could take, for example, big chunk of my space and map it here on the other small thing. So a map like that actually gives me some kind of distribution. Say my interval starts here. This is my I. Give me some kind of distribution with mass 1 on I, right? What do I want to do with this distribution? I want to average it out. and take phi of it. That's the left-hand side. Here, I first want to move this distribution via phi, and then average it out. Agreed? So let's draw phi. Phi is convex. Phi looks like that. Okay, maybe I want to take it exactly to here. Phi looks like that. Notice the following nice thing. First, what I have on the left is somehow the T0. This is the value that I have here. I would actually, in the proof, I would like to call it T0. Okay, this is the number in I, actually. We'll say second Y. It said that this is the middle of the mass. And this goes here. So what I have on the left is exactly this value here. Agreed? Now, on the right, I take this distribution and I push it via phi, right? For every element, I push distribution via phi. Look what happens when I start here. What happens to, say, this chunk if I go up? It was a very small chunk, but if I went up because of convexity, it becomes very large. Because my function looks like that, it becomes very large. So the distribution that I have here is somehow stretched above a bit. Okay? And therefore, the average of the distribution that I get here would be higher than just taking the middle here. So this is a proof of Jensen inequality. How would I make it into a real proof? So actually, it's more or less really a proof the minute that I draw another thing and I assume that this is continuous, this is differentiable. Let me draw one thing. I take the middle of my mass, and okay, let's start the real proof, but still with the picture, the real proof. I define T0 to be the integral of f d mu, right? So what's there inside, as written there? Can you tell me why this thing is in I? Why is this thing in my interval? I could have asked you at the end of the proof, where did I use the fact that it, yeah.
Because F maps to I and D is a probability measure?
Exactly. This is the only place actually where I use this probability measure. It maps to I. It can go higher because it's an average of weight 1. So yeah. So every value is there, and I take the average of weight 1 there. So this is in I. So what I would like to do, okay, this is the, let's make a stop here for the real proof. We'll go back to the other proof. I would like to take the tangent here. And this has the property that it's always below. Yeah? My phi is continuous. I don't know if it's even differentiable there. Sure, but if it was differentiable, I would have liked to take here the tangent. And then actually, this gap here is the thing that's giving me gap there. And this trick thing would be strictly, so the fact here is that this point that I get here is exactly if I take this mass and move it via my tangent, I would go here. But because I'm moving it via something that becomes larger and larger and larger, I'm getting this inequality. So the whole proof is just to define this tangent and see that it works. I think because I did it with so much details, it makes sense to finish the proof. So let's do the real proof. So this is good, this we did. And there is a stupid case where T0 is an endpoint. But if you figure out what do I need to do if it's an endpoint, there's nothing to prove. Okay, if you just plug it, you see that actually there's nothing to prove. So we assume that T0 is in the inside of this interval, and then we really have this picture. Okay, the mass is somewhere here in the picture. And now, what I want to do now is exactly the definition of this slope beta. Okay, it's not the angle. It's like the slope of this thing Yeah, actually, that's a good idea. This I do with my engineer students. How would I, they are much better than you in doing this. How would I write this, this line? I think I'm getting better on that. This would be b of x, beta, the slope of x minus t0 plus phi of t0. Yay. Right, this is the point here, plus what I get by this. And now beta is defined as my slope. Agreed? This will appear in the proof. So my goal now will be to define this beta without saying, if it was differentiable, beta would have been phi prime of that point. But if it's not very different. I define beta to be the supremum of all the differential quotient for s which is smaller than t0. So phi of t0 minus phi of s, t0 minus s. I take the supremum of all possibilities for differential quotient, even if it's not continuous, supremum is always defined. Okay, so this I define as my beta. And then I notice from convexity, so this is, if you want, this is the left-hand side derivative, always. And if it doesn't exist, it's still, I can call it the left-hand side derivative, okay? And what I want to show you is that it's always bigger by convexity from the right-hand side derivative. So it's always, smaller by definition from the right-hand side derivative. Manfred would laugh at me that I didn't do so much. Whatever. So convexity will tell me that if I take the infimum now for all the u's which are bigger than t0, right? You remember? I had this, I killed it. It was just here. The nice thing, it was this like t0 and u from that side. So if I take this infimum, and now the same thing, the differential quotient of u phi of t0 u minus t0, the thing that I erased, which was the reformulation that we said that after changing a bit of that, do you know what I'm talking about? Right? I did display of using this to generate weights, and the thing I just erased, this would and this is what I mean by convexity here. This would just imply that this infimum is always greater or equal to beta. Okay? This is what the thing that we had before, after saying what convexity is. And this will be for every, this is bigger for every u. So the infimum is always bigger. And then, so indeed, by indeed, I mean this is the intuition that we have from here. If I now take for every, this is a bit confusing, but I followed the book, so it will be easier for you to compare. Now I take for every S in I, not someone this smaller, every element in there, right? U or S or anything, I have the following. I have that phi of S is actually bigger than phi of T0 plus S minus, let's not be stupid, let's call it X. In the book it's S, what do I care? X times beta. Did you see this function somewhere? This is the linear function there, right? This is this tangent with beta, even if it does not exist. So I'm always bigger or equal to this tangent thing, okay? And the only thing which is, so let's check it. If I take S somehow to be below T0, then what is written here? Phi of S minus phi of T0 is bigger than blah, blah, blah. This is just by the definition of beta. right? So to prove this now for x smaller than t0, this is definition of beta, just by definition. And to prove it for x bigger than t0, this is just what we have here, is star. Just rewriting of that, and then we are actually done. We can just integrate and find the right place that I didn't throw this up. Right, so integrate. If I integrate, or I can move this all to the other side and say this is bigger than 0. In any case, if I integrate, I get something, the integral of phi of x, yeah. Yeah, and again I use actually probability 1. Here I get again it's bigger than the integral. Yeah, it's bigger than this value because I have a probability measure. Yeah, and the integral of this value, which is t0, which I actually get it to be 0, right? So this integrates to t0, so it vanishes. So I actually get this, which is what I wanted. This is phi of the integral of f d mu. Okay? So this is exactly what I wanted. I missed f at some point. And you didn't complain because it was too quick. This is for every x in I. Okay? Now I see why they didn't use x. This is now an element in I. But x, we have a space named x. Why would I call points not x? So for every element that looks like that, this is an element of I. So whatever f of x is, I have here f of x, and I have here f of x. Okay? And this also helps me to compile. And this is true. Okay? Right, remember my situation. I have x, f of x is element of I, and then I can do this business. You have the picture still here. And now again, let's integrate it. Then here, I get phi of x d mu. Here again, it's a number, and it's a probability measure. I get this one. Here, now I really get t0 before it was not correct. I get, so right, t0 was defined as the integral of that. So now it's actually also correct. Okay, so, and this is for convex. If I want to prove it for strict, then, wow. Then it's very similar. I just need to be a bit more afraid when I define this beta. Let's at least prove one thing, which is the maximality of entropy, and define the information function. I think that would be a goal, a reasonable goal for today. So lemma. This h of p1 up to pk, which is any partition with k elements of my probability space. This is the entropy of it. Okay, is bigger or equal, so it's smaller or equal to logarithm of k with equality if and only if pi is 1 over k for every I. Okay, that's what I want to prove, which was free of what we had before. Let's do the proof. As we said, phi of x log x with a minus is convex. Okay? If it's convex, then I can do the following trick. I can ask, what is phi of 1 over k? right? If I want to ask what the phi omega, okay, that's not very difficult. That's minus 1 over k log of 1 over k. Good, but phi is convex. And I have my partition element, the measure of my partition elements. So this is also equal to phi of the sum over 1 over k pi. What do I care? The sum is 1, I put 1 over k inside. Right? So if you want, I have my pi's and I weight them each by 1 over k, and this is a convex sum like that, so I can use convexity. This will be just, I taking the same weights and I apply this only to pi. Okay? This is convexity. Agreed? Okay. So we are almost done. Do it here. What is this thing? This is, I can take 1 over k out, doesn't care. And here I have pi. No, sorry. Here I have, minus pi log pi, because it's the definition of phi. Okay? And now it's the difficult part. This minus goes away. This 1 over k goes away. So this is smaller than that thing. Maybe I don't want to take the minus. Let's not take the minus over. The 1 over k goes away. The minus, let's leave it. Then this is actually is equal to log k. And I managed to do something very stupid, apparently. This is a minus, good. So now I multiply by a minus, and I get the other inequality. Let's not wipe things out, so I'm not confused. What was there before? 1 over k log of 1 over k. That's correct. And here I have that thing with 1 over k. This is bigger than that thing. Please help me. I want to show that the entropy is always smaller than.
Why did you put the minus sign into the phi? Wasn't it just x log x?
I think, yeah, that might have been my mistake.
And then it's concave instead of.
Right, otherwise it will not be even convex. Thank you. Yeah, thank you. That was wrong. And that makes sense that I don't, then this is also not here. Now, maybe I put the minus inside. That would be okay now. I take this out. I take this out. Okay. And I can put a minus, I can multiply by a minus, so I get, let me write this out, multiplying by minus 1. Then I get minus of log 1 over k is bigger or equal to minus of pi log pi. This is the entropy of the partition p k, and this is indeed log k. Okay, thank you. I don't know who was it, but maybe you got it back now. Okay. Maybe let's do one last definition. The most important thing what I was sure that I would do today is proposition 1.7, which shows a lot of, so it proves all the basic properties of entropy. And actually, the right way somehow to prove this thing is define another function, which is called the information function, because it gives us a bit more measured theoretical point of view on such things. It's quick to define, and then we go, at least I go to the theme lecture. I Normally it's good lectures, not always, but normally it's a good lecture. Information function, so in some sense, right, I had this pi, which was the weight of my atom, and log pi. The information function is only this log of, yeah. So let's define it. I have a partition, information with this position, and I want to define a function, which is the information function. Yeah, so I will define it to be the amount of information that I see in the atom of X. This would be always defined with respect to a measure, be minus of the log of the atom containing my element X. And then notice the amazing thing that this we can still do. What is then the entropy of a partition? Amazingly enough, it's the integral of the information function. Why is that? So this information function is constant on atoms. It doesn't change on the atom. So what do we get from one atom? We get the measure of the atom, right? Times the value of the function, which is exactly this P1, if this is the measure of the first atom, times the log of P1. And the same for P2, and so on. So, and this also makes sense if we want to measure information. This is like a local object. It's a function, a measurable function. This is measurable. Measurable function that measure for us the information, and it makes, this is the only possible definition if we actually measure total information. Okay, yes? Should, where it's not? Ah, yeah, this doesn't make sense, right? It's very shame that I forgot the, yeah, this is good. Forgot the chocolate. And the minus is also there, so it will be positive, right? Because always between 0 and 1. Yeah. I guess, thank you very much, and sorry that I didn't do the whole course. Manfred will do it quicker. Good. Don't tell him. Good. Thank you. So who is coming to the apéro? No, who is coming to the lecture? To come to the lecture. Yeah?
How long is the lecture?
45 or 1 hour? Good. I was just interested. I'm not sure how much it's one-to-one, but normally the idea, what we tell them is that it should be for all students, definitely for second, third year students. So if they listen to us, it's a different question. So, but I have a good feeling. So please come. Thank you. Yeah.